Okay, so I'm going to state it again because the recorder wasn't running. But like I said just moments ago, Q equals MC delta T is the equation we use to determine what happened in terms of energy to the surroundings, in this case, the water. You may have encountered some questions on that sheet, and I'll ask you, were there ones that had you calculate it for something other than water, like maybe iron or something like that? Yeah, so we can calculate Q equals MC delta T for any substance. But in this course, the surroundings that we're going to use predominantly will be water, because we're going to be looking at chemical reactions that take place in solution. So if we now have a chemical reaction and we notice that the temperature of the solution changes, we should be able to calculate how much energy that water gained or gave off. And that's what we've mastered. But as chemists, the surroundings isn't very exciting. As chemists, we want to know what's happening to the chemical system. We ultimately, as chemists, want to know what's happening with the bonds of the reactants and the bonds of the products, and we want to be able to understand energetically why something's gaining energy or how much energy it's gaining or how much it's giving away. So today's lesson is about the system. Enthalpy is all about the system. So let's define enthalpy, and then I'll explain how it works. Now, just write down the first bullet on this. Just write down this first bullet. And that's because the second two we wrote in the last lesson that we had in class. In the last lesson, we talked in great detail about kinetic energy, the energy stored in the motion of the particles. That can be vibration, rotation, and translational motion. And we talked about the potential energy that's stored in the bonds. Remember, I said it was electrostatic potential energy. You didn't have to worry about that. But it's the bonds that are holding those atoms together. And in a chemical system, if you take the total amount of energy, the kinetic energy, the energy of the moving particles, and the potential energy, the energy stored in the bonds, and you add them up, you get what we define as chemists as being enthalpy, all right? And I'll talk more about the term enthalpy just in a moment. So in that little movie, that other one I asked you to watch, when you think of the system as being a bank account of energy with kinetic energy and potential energy all in one in the system, we're now defining that as chemists as being the enthalpy, as being H, okay? Are we okay with the term enthalpy as being defined as the kinetic energy plus the potential energy in a chemical system? It's a very straightforward idea. Now, it turns out that just the enthalpy H is not a very exciting number, property. It's not very useful. And that's because if a chemical system isn't changing, if it's just sitting there, then the enthalpy is constant. The exciting thing about chemistry is when a chemical change takes place. So enthalpy is not very exciting because that means chemistry hasn't happened. But once chemistry has happened, and we have a chemical change between reactant and product, it means that the enthalpy of the reactant will be different than the enthalpy of the product, and we will have a change in enthalpy. So, I'm going to repeat it again because I was speaking as you were writing. The enthalpy, H, is the total of the kinetic energy and the potential energy in a chemical system. The enthalpy isn't that exciting because it means chemistry isn't happening. It means something isn't changing. But if we have a chemical reaction and reactants become products, it means that I may have different amounts of potential energy in that, and the enthalpy may change. So as a chemical reaction takes place, if there's less potential energy in the products, then that enthalpy may go down, and I will have a change in enthalpy. And I'm going to get you to draw a picture like this in a moment. You don't have to draw it right now, but I'm going to get you to do that. So it's the change in enthalpy that's really important, all right? Now, how do we calculate the change in enthalpy? Well, if you've taken physics, you might think that it would be as simple as taking the final enthalpy and subtracting the initial enthalpy, just like I did with delta T. That would be a correct equation. But it turns out that there's no experimental way to determine the actual enthalpy. There's no way to know what this value is. And there's no way to know what the final enthalpy is. It has to do with some funny laws of physics that deal with when we cool the system down to absolute zero. There's no way to determine exactly what that first starting energy is. It's called the Heisenberg uncertainty principle, and it states that you can't determine the position and the motion of a particle simultaneously. It essentially means that there's this inherent uncertainty to that total enthalpy. But it turns out that we don't need to know the enthalpy. We just need to know the fact that the enthalpy changes. Again, think about it like a bank account. Because we are not obscenely rich people, who knows, maybe Scott is obscenely rich, we don't know that. But because most of us are not obscenely rich, we know exactly how much money is in our bank accounts, and we're very, very, we watch it closely so that we don't, spend too much money. But if you were Justin Bieber, obscenely rich, Justin Bieber probably has no idea how much money he has in his bank accounts. But it doesn't matter. All that really matters is that he knows how much money he takes out and how much money he puts in so that he never gets to the bottom of the bank account. So if you are obscenely rich, you don't care how much money there is there. As long as the amount of money that goes out is about equal to the amount of money that comes in, you're going to be fine. You're never going to get to the bottom of the bank account. So the actual size of the bank account has no material except the change, right? I want to buy that Ferrari. All right, bang, they're down that much. Okay, I'll just put out another single on YouTube and do a concert, and boom, I'm back up to here, right? So it doesn't matter the total amount, just like our energy situation. It doesn't matter how much energy there is in the system, but it's the change that really tells us something exciting about the chemical reaction, all right? So even though I defined H moments ago, we will never be talking about just enthalpy. It'll be the change in enthalpy that's what we're really worried about. Okay, now, I am going to get you to draw this. I'll tell you right now, in the past, I used to hand out a sheet, and I actually did photocopy it for today, that had 5 or 6 different versions of this picture, and I explained it in different detail. I'm simplifying this. I realized when I did this lesson this morning, there's no need for me to go into so much detail. So I do want you to draw this picture, and I'm going to annotate it for you so that we can make some sense out of it. So what does this picture consist of? This is much like that little lesson I had you watch as well yesterday. It talks about the surroundings as if it's got a certain account, and it talks about the system, and it has a kinetic energy account and a potential energy account. The kinetic energy are the particles moving, and the potential energy is the energy stored in the bonds. Yes? There was a second video that I put on there that was called System versus Surroundings. If you didn't see it, you can go back and watch it later. It's not mandatory that you have it to understand this. If you've watched it, great. If you haven't, you'll be fine. It's not a big deal. All right? And like I said, I used to do a big, long explanation on how this works, but I am going to just simplify it because it doesn't serve the purpose that I want it to go into so much detail. Very simply, and I'll go with a darker color here, very simply, in an exothermic chemical reaction, potential energy is converted to kinetic energy. So the amount of potential energy comes down to there. So potential energy is converted to kinetic energy, which makes the system hotter. And when the system is hotter, that potential energy is given to the surroundings, and it's given to the surroundings as Q. It's that simple. During a chemical reaction, stored energy in the bonds is decreased. It's turned into kinetic energy, which is heat, and that extra heat is given to the surroundings, and the surroundings catch the heat. This results in a negative delta H, because my H was here and now it's down there. It's like we've spent some money. And that money appears over here and warms up the water. And so we then see this as being MC delta T. Okay? So in an exothermic reaction, the system turns some of its bond potential energy into heat, and that's given off to the surroundings. We know how to deal with the surroundings. We did that yesterday. So now it shouldn't take much for us to take that Q that the surroundings has, change the sign, and say, we know what happened to the system. It gave up this many joules of energy. Okay? We can't actually see what's happening in the system because we don't have the ability to jump in a magic school bus and take a look at what's happening to the bonds. But we can sense what's happening to the surroundings because I can use a thermometer and a scale and the heat capacity, and therefore I can use the surroundings to tell me about the system. Okay? And this is the equation. I'm going to show you an equation later on, but I'm actually going to jump ahead a little bit. This is the equation you're going to see in tonight's flipped lesson. The relationship between Q and delta H, you'll notice that they're opposite signs. Because of the conservation of energy, the amount of energy this thing gave away has to be equal to this energy. So negative Q is equal to that enthalpy change. If the surroundings got hotter, it means that the system had to give up some energy. So if the bank account of the surroundings, which would be just the bank, goes up, then your goes down. All right? So that's an exothermic reaction. Any questions or concerns? All right. Picture looks the same as the last one. I have a different level for the EP because what do you think is going to happen to the energy of the system in an endothermic reaction? It's going to go up. So in an endothermic reaction, more energy is going into storage. We're storing more energy away in the bond. Yes. Yeah. In the way in which I taught it in previous years, I explained in more detail the complex relationship that exists between the kinetic energy and the potential energy, because there's this transfer and then energy moves in and moves out and all this other stuff. But in the end, it is simply the potential energy that changes after all of these other changes happen, right? So there's lots of complex changes that actually happen, but in the end, it's only the potential energy that changes. And I used to teach it that way, and I think I just confused people more by having them think about what was happening in the complex interactions. And now I feel it's not useful to this course. So I'm just saying, in an exothermic reaction, the potential energy goes down. Where does that energy go? It comes out into the surroundings, and the surroundings get hotter. Okay? All right? In an endothermic reaction, the chemical reaction takes place. It stores more energy in the potential energy form. That energy has to come from somewhere. It comes at the expense of cooling down the surroundings. So the energy that gets stored is at the expense of the surroundings energy, so it sucks its energy up. And this time, the surroundings get cool. They cool off the surroundings. Again, this is measured as Q. Again, this time we have a positive delta H. And because the temperature is going down, in this case, your Q number will be negative because I'm going to have a drop in temperature, and T2 minus T1 will be negative. So again, it means we can just use the same equation. Negative Q is equal to delta H. So that's a standard equation that we can use. So now what have we done? Well, you've mastered Q equals MC delta T. It now means if we've got a chemical reaction sitting there, we now know what's happening to the system. It's going to gain or lose energy, and it's got the opposite sign to what happened to the surroundings. Okay? If we knew nothing about chemical bonds, we would think that this system is simply sucking up thermal energy or spitting out thermal energy. It looks as if it's just sucking up heat or spitting out heat. All right? Enthalpy means heat within, right? The term energy comes from energon, which means work within. The inner part is within, and then ergon is work in Greek or something like that. So energy means to have work within it, the ability to do work. Enthalpy means thermal energy within it. There seems to be some thermal energy in there, and at some point during a chemical change, it spits out some thermal energy or it sucks up some thermal energy. We now know that it's being stored as potential energy because we now know about bonds and atoms. But before they knew about bonds and atoms, they knew about energy changes. And so they just said, there's some source of thermal energy in there that's kind of stored away, and when a chemical reaction takes place, it either spits out some thermal energy or it sucks it in. And hence it's called enthalpy. All right? Okay. So let's just write a little bit down officially about this instead of the picture. We'll write it in some words and symbols here. So again, I'm stating the same thing as I just did, except the other one was graphically, right? If the EP stored in the product is greater than that of the reactants, it means I've put some energy in. The level of the potential energy bank account went up. Then it is endothermic. Then we say the enthalpy of the system increases. The enthalpy went up, or the delta H is greater than 0. The positive value, that change. Even though we don't use the symbol H, we still talk about the enthalpy as being that total. So an increase in enthalpy, we're storing some. We say then the delta H is greater than 0. I often like to write it as delta H is positive. All right? Greater than 0. Yeah, you guys struggled with the greater than and less than last year? Yeah, remember the pH, we struggled with greater than and less than? I don't know. Some of us do, some of us don't. The delta H is positive. It's going up. Okay? And I've got an exothermic slide that looks just like it. And if the energy stored in the product bonds is less than the energy stored in the reactant bonds, then as we go from reactant to product, it's coming down. And the enthalpy of the system decreases, or we say that the delta H is negative. And really, this statement and its equivalent on the previous page of delta H is negative, that's all I really need you to get out of this at this point. That's the important way to think about it, because we'll be doing math, we'll get a delta H, and if you see a negative sign, you need to think the bank account coming down, and you need to think exothermic. That thing's giving off some energy. If you see a positive sign, you need to think the system is endothermic. It's gaining in energy. That actually now, at this point, allows you to finish the question here, right? Because what happened here in this number 3 in the textbook is we had a neutralization reaction, and the surroundings got hotter. They gained in energy because the temperature of the surroundings went up. If the temperature of the surroundings went up, what must have happened to the energy of the system? It went down, and therefore the delta H had to be a negative value. So how would we describe this particular chemical reaction, Corey? It's an exothermic reaction. So I put that question in the wrong position. You could do the Q equals MC delta T, but you didn't have the explanation yet in order to logic that out. Okay? Any questions or concerns at this point on that explanation? Okay. Let's talk a little bit about types of enthalpy changes that you can encounter. And this is just one of those information notes. There's no other way to sugarcoat it. You just need to write it down. So like I said the other day, we're not going to be quite as picky as, grade 9 and 10 teachers where physical changes are completely different than chemical changes. We're going to treat them as if they're all chemical reactions. Because we're going to want to study the energy changes when something melts or when something dissolves or et cetera, et cetera. So we can study the enthalpy change of a physical change. The bonds that are broken during physical changes are those intermolecular forces. You don't need to know them, but you need to just kind of be reminded of them. We will have to know them at the end of the course. But that's things like dipole-dipole interaction, H bonds, ion-ion interactions, right? If you're going to melt some ice, you got to break those hydrogen bonds that are holding those water molecules together. In chemical changes, we are breaking bonds, covalent bonds. You're breaking single, double, triple bonds, blowing molecules apart, having them reform, forming new single, double, and triple bonds. Now, we're not going to actually be looking at any nuclear changes, but just to bring it to the extreme, we can also, talk about the energy involved in a nuclear change. You undergo nuclear fission, the nucleons, the protons and the neutrons, they reorganize themselves, they give off lots of energy. There would be a calculation we could do with it. What kind of bonds are being broken there? Well, you'd be working against the nuclear strong force. Right? And again, if you have no idea what I'm talking about in terms of the nuclear strong force, it doesn't matter. But if you've taken physics and Mr. Petrus has mentioned the nuclear strong force, then that's that really strong force holding the nucleus together. That's what's providing the energy. So those are the various types of changes that can give off energy that we can deal with. I guess one of the bigger things on this slide is that the energy change in a nuclear reaction is always much, much greater than the energy changed in a chemical reaction, which is only kind of greater than the energy change in a physical reaction or a physical change. Okay? Yes, no? I can't tell if we're underlining or we're writing. We got some underlining going up front. Some writing. Jess is finishing off. No pressure. Excellent. All right. So now let's get down to the business of actually doing some calculations involving delta H. Now, there are 5 methods that I'm going to teach you on how we calculate this delta H value, this energy value. One of them is called molar enthalpies. Yes, we're going to be dealing with moles, obviously. And a molar enthalpy is like a molar mass, like a conversion factor. And we're going to be doing that for the rest of this class. Number 2 is calorimetry. Now, I've already given you the calorimetry equation. It's the negative Q equals delta H. It's whatever we measure in the system, the surroundings, the opposite happened in the system. And that's going to be your flipped lesson for tonight. And I still want to go ahead with this flipped lesson thing. I I want you to have a work period tomorrow so that I can help with both yesterday's stuff and tomorrow's stuff. But it's essentially putting together today's equation that I'm going to show you in a moment with Q equals MC delta T. It is not, again, difficult things. Then we're going to do a couple of experiments, Monday, Tuesday, and then I'm going to teach you about bond energies, and that's actually calculating individual bonds. Hess's law is a method of adding up multiple chemical reactions. You don't need to have a lot of detail on this. I'll show you all about it. And then ultimately, we're going to talk about what is called heats of formation reactions, and that brings us pretty close to the end of the unit at that point. So what is a molar enthalpy? Molar enthalpy, I thought I pushed that freeze button and got rid of that. So molar enthalpy is the enthalpy change, the delta H, associated when 1 mole of a substance undergoes a physical, chemical, or nuclear change. And we're not going to be dealing with nuclear, obviously. So now we're talking in terms of just 1 mole. A molar enthalpy will be kind of indicated to you by the fact that we've got a little subscript beside it, all right? Now, before I get into showing you what's on this table, let me just do a little quick review with you to just show you what we're really talking about here. And you don't have to write this down. Okay. If I have a, whoops, why doesn't the pen work with this? If I have, say, a mass. This is a review of mole stuff. Hopefully you started to look maybe at your stoichiometry review, and if you have, then you're in good shape. Let's say I had 10 grams of NaOH, and I wanted to convert that over to moles. How do I convert mass to moles? You guys are great. That's good stuff. Molar mass. All right. So I would use a molar mass. In this case, it would be 40 grams per mole. Does that sound familiar to everybody? We'd do a conversion factor thingy. We'd cancel some stuff out. Good times, really. Good stuff. And let's say I had the volume of a gas, and it was at STP, and I want to convert that to moles. Marika, what would I use? This is only fair, Marika, don't you think? What would I use? Molar volume, right? She just coming out of the grade 11, right? So she's got that in her mind. Remember molar volume, all that good stuff? I could use a molar volume, and I believe for STP it's 22.4. You don't have it memorized? I think it is 22.4 liters per mole. All right, notice how everything is per mole. And we could flip over. So let's say I had 10 liters of this. I could put it in and cancel out the liters and get moles, right? If I'm given some energy, or essentially an enthalpy, if I'm given an enthalpy, not a molar enthalpy, but just a total amount of energy that came out of a chemical reaction, let's say 10 kilojoules of energy, then how would I convert that into moles? Well, I wouldn't use a molar volume and I wouldn't use a molar mass. I would use a molar enthalpy, which would be the enthalpy that it would produce or use in terms of energy per 1 mole of that substance. So I would use, and I'm not going to write an MV or an MM, a delta H subscript X. So the little x is what tells you, and it doesn't have to be an X, I'll tell you what it can be in a moment, but that's what tells you that it's a molar enthalpy, and also the unit will tell you. So the molar enthalpy has to be determined by some experimental means, but let's say in this case that it's like 2.3 kilojoules per mole. I could then take my kilojoules and the molar enthalpy, and I could do some conversion factor stuff, and I could figure out how many moles I have. All right? So a molar enthalpy is like a molar mass, is like a molar volume, except it isn't just for a substance, right? Molar mass works for just sodium hydroxide, and molar volume works for a gas at STP. Molar enthalpies, you need to know the entire chemical reaction, because it's for an entire chemical reaction. But we can still use it in the same way. All right, I'm going to come back to that in a moment. Now, hopefully you've written C page 299, because this table is on it. And here are some examples of some different types of molar enthalpies. If a substance dissolves, goes from a solid to aqueous, in other words, we dissociate it, then that's a delta H of, and it says here, SOL, solution. But because it's a subscript on the delta H, that tells me it's a molar enthalpy. It's going to be per 1 mole of NABR. And if I'm burning something, then I'm going to have a delta HC, combustion. And notice the one in red, per 1 mole of CH4. And I could have vaporization, turning from liquid to gas, per 1 mole of whatever's being vaporized. And this is a delta HF. It's called a formation reaction. It's a little different than the rest of them. We won't worry about that till later on, but it's the energy needed to form 1 mole of a substance. But notice how there's always 1 mole, because it's a per mole situation. This is a heat of neutralization. We're neutralizing some sodium hydroxide with some sulfuric acid, and in this case, it's per 1 mole of sodium hydroxide. But in the second case, because I've divided everything by 2, it's per 1 mole of, sorry, that's sulfuric acid. This is sodium hydroxide, okay? We'll work more with those a little bit later, but I do need you to know what those little symbols represent, that a C is combustion and V is vaporization and F is formation. So you don't need to write that table down, but you've got the reference there, okay? We'll be talking about these different reactions in a little more detail in a bit, okay? Let's now do some simple introductory calculations. You don't have to write this underneath here, folks. I'm going to annotate this slide by just using my arrows and defining everything. Don't write the moles and the delta HX. I'm going to define everything. Don't write these bullets down here. So essentially, here's what I'm going to do. Once you've got the equation, I'm doing this. Whoops, not in black, that's for sure. This is the total delta H, total enthalpy change, enthalpy change. All right. And that's for not just 1 mole, but it could be 5 moles or 10 moles or 2.5 moles or 0.3 moles. It's just the amount of energy, the total energy. And that is typically in kilojoules, but it can be in joules. This is the molar enthalpy. You know what, we don't usually say change because we know we can't deal with just the total enthalpy. Usually we just say molar enthalpy or just total enthalpy. We don't even say change, but it truly is. It's a delta. Molar enthalpy, you tell me what the units have to be. If it's per mole, if it's molar, what are the units going to be on this thing? Yep. Yeah, or, yeah, kilojoules per mole or joules per mole. And what's the N? Yeah, it's moles. Moles. Okay? Now, in the previous courses, we used everything as conversion factors, but you could write down equations for all of these, right? So in this case, delta, right? Delta H is equal to N times the molar enthalpy, delta HX. In this case, the volume would be equal to the molar volume times the moles, right? And in this case, the mass would be equal to the molar mass times the moles, right? Everyone has its own equation, but we just use them as conversion factors, right? But you could do everything with equations as well. In this, we're going to just stick to equation. Well, we're going to do an equation first, and then we'll use it as a conversion factor. I'll show you how to do both. Okay. So essentially, I've got 3 examples. I might just hold it to 2, so I can give you a little heads up on the lesson, the flipped lesson for tonight. Now, molar enthalpy is like a conversion factor. I will supply you with that information unless I'm asking you to calculate it. Because in theory, I could give you any 2 of those variables and ask you to calculate the other. This is a classic 3-variable equation like you learned in physics right at the beginning, a nice easy one. You know what I'm talking about? You get 2 pieces of information, solve for the third. So notice it says, determine the enthalpy change. What am I looking for in my equation if I just want the enthalpy change? What do you got? Just the delta H. That's not the molar enthalpy, it's the enthalpy change. So I'm looking for delta H equals N times delta HX. This is a nice one. I've got 5 moles. And now I need the molar enthalpy of freezing for water. Now normally I just give that to you. I give you the number. This came out of the old textbook, so I'm just going to keep this table here. There's water. This is the molar enthalpy of fusion. Fusion is the term we use to describe melting or freezing because it's the same process except it's opposite, right? So the number here is 6.03 kilojoules per mole. 6.03 kilojoules per mole. Okay? Now there's one thing missing here, and that's the sign. And we need to think a little bit about this one. If I have liquid water that has a high energy content go to solid water that has a low energy content, what has to happen to the energy within that water? Do I have to gain some or do I have to lose some? Are you going to answer my question, Corey? Okay. You'd lose energy, okay? So in other words, some H would have to leave. So what would the sign be of my molar enthalpy if I'm freezing something and the energy is coming down? Yep, negative. It's negative because I'm going from a high energy state to a low energy state. So I need a negative. All right? Yep. Yes. Yep. Fusion is melting or freezing. It's just the sign is different depending on which way you're going. That would be to boil it. That would be to boil it. Or to condense it. To boil it or condense it. Either way. You'd have to pick the sign whether you're going from high energy or to low energy. Okay? All right. Well, now we've got 5 times negative 6.03, which isn't too tricky. Somebody got it? What do you got, Megan? 30.15 kilojoules, 2 significant digits. So it's looking like negative 30 kilojoules. And if I want to get rid of the ambiguity of that last significant digit, 3.0 times 10 to the 1 kilojoules, because now I know it's 2 significant digits, right? Again, I don't need that last step, but that's the proper way to do it. If you want to get into the groove and you get good at it, it's great. Okay, let's just do one more. So now instead of moles, I've given you a mass. This is just like stoichiometry all over again, except now we've got a new conversion factor. What am I gonna do with that mass? What am I gonna do with that number? We've got to be able to be starting to think like this, because if I'm given a mass and I don't want to deal with masses because I don't know what to do, what do I always convert it into? Moles. You're going into moles. So we're gonna go mass to moles. And then once we have moles, we could stick it in the equation with the molar enthalpy. Or we could just use it as a conversion factor. So let's try that. So I'll make a little map, just like the good old days. If I want to go from mass to moles, what's the conversion factor to go from mass to moles? Oh, you guys are great. You guys are great. This is fun. How do I go from moles to delta H? The molar enthalpy, the delta HX, right? We can do that in one shot. Let's get rid of the kilo. 1.5, what am I turning the K into? Times 10 to the 3 grams times 35.5, 23, 58.5. Notice I'm looking at the clock and I really don't care if you know what I'm doing at this point or not. Watch the movie. I've turned it into 58.5 grams per mole. I want to get rid of the grams. 58.5 grams per 1 mole. Now we're in a new territory. I need my delta HX. So let's write that off to the side like we would write any conversion factor. I am melting sodium chloride, so I want fusion. Sodium chloride is right there, 28 kilojoules per mole. 28 kilojoules per mole. We're melting it. We're going from a solid up to a liquid. So what sign will there be here? It'll be positive because the energy is increasing. And now I can put that right into here. Grams are gone. I want to get rid of moles. 1 mole per positive 28 kilojoules. And in the end, that's going to get me how many kilojoules will be produced or will be required to do such a move. 7.2 times 10 to the 2 kilojoules, and Corey's going right to significant digits in scientific notation. He's showing off. Nice job. But if I recall from this morning's lesson, it would have been a 718, I believe. Correct? And then rounding it to 2 becomes a 720. And then putting the icing on the cake makes it 7.2 times 10 to the 2 kilojoules. So we can use it as a conversion factor as well. Okay? I'm not going to do the last example just for the sake of speed. There are 3 little questions that you can do just on that molar enthalpy equation.